So the topic for this video is truly fantastic and it's truly very deep. We are going to discuss Russell's paradox and how it is a massive problem for naive set theory, and then even better, this horrific paradox that seems unsolvable and makes you want to despair about the foundations of maths. It actually has a way around it, it has a solution, and that solution is axiomatic set theory. That solution is Zermelo-Fraenkel set theory, and that then is going to be the topic for this video. So if you watch this video to the end, you will understand how to get around the problem of Russell's paradox. So let's start by stating prerequisite knowledge. So basic knowledge of naive set theory is a prerequisite. Now, if you're sitting there in alarm thinking, oh gosh, what's that? Don't worry. Anyone who has clicked on this video and is interested in learning Zermelo-Fraenkel set theory almost certainly will have basic knowledge of naive set theory. So naive set theory is all of the set theory you know already before learning axiomatic set theory. So this definition here is actually Cantor's original definition of what a set is. So it's a well-defined collection of distinct objects. And hopefully that's your intuitive understanding of what a set is as well. Other things that you should know from naive set theory, you should understand what it means to union two sets together, what it means to intersect two sets together, and what it means to take the relative complement of B within A, where of course this means take all the elements in A and subtract out the elements that are also in B. I also have a preceding video to this one in my playlist on set theory, which is about the proof that the cardinality of the power set of a set is never equal to the cardinality of the original set. And I would like you also to understand that prior to watching this video. So if you know that already, you don't need to watch that preceding video. But if you don't know that and would like to see that diagonal proof, then please watch that video before proceeding to this one. So when naive set theory first came about, everyone was very excited. It looked fantastic. It looked as though we were going to be able to use this as the foundations for all of maths. All of the formal systems that we want to define in maths, they could be fundamentally thought of as sets. So for instance, all of group theory and then all of abstract algebra comes from sets. When we define groups, we start off with, let's start with a set of symbols and then we'll define the composition law on top of that. And then all of our classical algebraic number systems, which I have put here, so the natural numbers, the irrational numbers, the real numbers, and the complex numbers, all of those could fundamentally be thought of as sets with then these additional algebraic composition laws defined on them. Other things like order, metrics, which we use for analysis, all of that could also be thought of fundamentally as you start off with the set and then you define these additional properties on top of it. So it seemed extremely exciting that we could use this as the foundations of maths, and indeed we can still use it as the foundations for maths, but there was a massive spanner thrown in the works when Russell came along and showed that there was potentially a massive inconsistency in set theory. So before Russell's paradox, in naive set theory, there was an unwritten axiom or an unwritten assumption, and it's only been given a name in hindsight now that we realize how bad this assumption that they were making was. It's now called the Axiom of Unrestricted Comprehension. And what this means is that people believed in naive set theory times that you could define a set using any rule that you liked. So for instance, you could make the set of all things that were red. That was a credible set. You could make the set of all things that have the letter I in them. That was a set. So you could make these sets according to whatever rule you wanted. You could define a set with whatever rule you wanted. That's why it's called unrestricted comprehension. So the defining of sets had no restriction in rules that you could make that they needed to obey, or the elements inside them needed to obey. This leads to Russell's paradox, which was concocted by Russell. And this is the innocent looking set that breaks this axiom or makes this axiom totally inconsistent. So R for Russell's set, and it's defined to be equal to the set of elements X where X does not contain itself. So the elements of this set are going to be sets themselves. So just to explain this a little bit better, let's take a concrete example. So here we have the set S, which is the set containing two elements, 1 and 2. And you can see that neither of these two elements are equal to the set itself, so this is an example of a set that does not contain itself. So congratulations to the set S, it would meet the criteria to be a member of Russell's set R. Meanwhile, poor old set S prime here is the set containing 1, 2, and then you can see I've put in S prime itself inside the set. So S prime is an example of a set that does contain itself, and it would not meet this criteria for admission into Russell's set. So Russell's set, therefore, is the set of all sets that do not contain themselves. Now, why is this a problem? Well, you can then ask the question, is R inside this set itself? Does this set contain itself? And the problem with that is there can be no correct answer, because if the answer is yes, if R is inside itself, then it shouldn't be inside itself because it doesn't meet the criteria to be inside itself, which is not containing itself. If it were to be inside itself, it does contain itself, and therefore it doesn't meet this criteria. On the other hand, if R is not inside itself, then it doesn't contain itself and it should be inside itself. So it can neither be inside itself nor outside of itself, and that's an inconsistency. So you might think this is just silly, why would I ever want to define a set like that? However, if you work with this unwritten axiom that people were assuming in the times of naive set theory, that you could define a set according to whatever rule you like, then this is a perfectly credible rule. But defining a set like that leads to severe logical inconsistencies where this set R can neither be inside the set nor can it not be inside the set. And here is why this is such a big problem, why this threatened everything. Because how do you know in maths, if you're basing all of maths on set theory, how do you know that when you, for instance, define a set like this one, so the set of all elements X such that X is an element of the complex numbers and X satisfies this equation, how do you know when you define that set according to these rules? You've made a rule here. Using this axiom, you can use that rule to define this set. How do you know, though, when you define that set that you want to use in maths, that it isn't subject to the same logical problems as this set? How do you know that there aren't things that can neither be inside this set nor can they be outside of this set? How do you know that all of this maths that is based on set theory isn't going to have the same inconsistencies as Russell's set up here? So that, ladies and gentlemen, that is the problem for this entire video. That is the motivation for all of axiomatic set theory. Trying to get rid of this problem of Russell's paradox, trying to make set theory consistent once again. So how do you resolve this then? Well, some people might find this a little bit unsatisfying. The way you resolve this set is that you say it's not a set, you banish it from set theory. You also banish this axiom that allows this set to be a set from set theory. So you want to define set theory freshly, and that's what Zermelo-Fraenkel set theory is going to be. And in this fresh definition of set theory, you want it the case that 1, this is not an axiom, and 2, this is not allowed to be a set in your fresh definition of set theory. So one way that you could imagine doing this is you could start from the top and work downwards. You could imagine trying to write down a list of all the things that are banned from being sets, and for instance Russell's set would be one of the things, or sets of that nature would be in this list of things that are banned from being sets. But that's very, very difficult, because how do you know how many different sets there are that potentially lead to logical inconsistencies. We've got this example, but what if there are other ones out there? So it's a very difficult task to do that, and you never know whether you're going to actually be finished if you were to create a list of rules of things that are banished. You might just have to add more things onto that list as more people come up with paradoxes forevermore. So instead what we do is we start at the bottom and we work up. So we start from the very basics and say what we're going to allow to be a set, and then we build other things that are allowed to be sets out of those things that we've started with. And I'll show you how we're going to do that. And that is all of what Zermelo-Fraenkel set theory is about. And the axioms of Zermelo set theory are what are needed to be able to build the more complicated sets that we want to be allowed, i.e. the sets, for instance, that are shown over here. Now, we're not going to discuss all of the axioms of Zermelo-Fraenkel set theory because some of the later ones are actually very complicated, and they come from you needing these more complicated number systems to be allowed to be sets within set theory. We'll do those in later videos in the playlist. We'll just start off with the basics. The main point of this video is to communicate the whole motivation, the whole ethos for Zermelo-Fraenkel set theory, which is to try and get around Russell's set being allowed as a set by building from the very basics what we're going to allow to be sets. So in this video, we'll look, for instance, at the natural numbers, and we'll look at the axioms that allow the natural numbers to be a set in this new, freshly defined set theory. So let's build Zermelo-Fraenkel set theory then. So before we begin, let me just say that we're not going to change the definition of a set or what it means to be the element of a set. When you are going deeper and deeper into maths, there is a limit to how deep you can go. At some point you do have to stop, and many mathematicians choose this point to stop. They choose to assume that everyone intuitively understands the definition of what a set is and what it means to be the element of a set, and they don't try to define those further. Because if you start going deeper and deeper and deeper, eventually your definitions just become circular because you're going so deep that actually to define something, you're using the thing that you're defining to define it. So it loses any sort of purpose to go that deep. So we will stop at that point. We will assume that everyone intuitively understands the basics of what a set is and what it means to be an element of that set. And now, in our new, freshly defined set theory, Zermelo-Fraenkel set theory, we're going to define what sets are actually going to be allowed in this theory. So, axiom number 0, I've called it. This axiom is often just omitted, so you often won't even see it, but I like to start with it because it is a very simple one and it gives you the starting point for which sets are going to be allowed. So this axiom, if it is defined in your textbook, will be called the empty set axiom. So here's the symbol for the empty set, phi, and it just means the set that contains nothing. And the empty set axiom is basically that this set is allowed in our new theory. It's going to be accepted as being a set. So there we have at least one thing in our new theory that's going to be allowed as a set. Axiom number 1 then, the next one. This is called the axiom of extensionality, and this one you will always see. No matter which textbook you go to, you'll always see this, usually as axiom number 1. And this is a really big, horrible name for something that is incredibly simple. And it says that if two sets that are allowed in our new theory, so let's presume A and B are sets that are going to be allowed in this new theory, if they're the same, it simply means that all the elements within them are the same. So this is true if for all x is an element of A, x is an element of B, and for all x is an element of B, x is an element of A. That's all it says. Two sets are the same if their elements are identical to one another. I don't know why it's called the axiom of extensionality. It's not what I would have called it. I think it means that it's about the extension of the set, the elements within the set. but I would have called it something like the axiom of identity rather than the axiom of extensionality. However, that is its name. So not a particularly deep axiom, however, nevertheless, very important thing that we are taking as true about sets. So it is an important thing to have formally written within our axioms. The next axiom then is what we'll call the power set axiom. And this says that if you have a set A that is allowed within our theory, then the power set of that set A is also allowed within the theory. So it's okay, you'll let that be a set as well. And this is actually why I wanted you to know the result from the preceding video in my playlist on set theory. So that preceding video, remember, was on the cardinality of the power set and how it's never equal to the cardinality of the original set, even if that original set is the empty set, because that then gives you the logical basis for understanding that the power set is never going to equal the original set itself. So this axiom, therefore, allows you to always create a new set that is allowed within the theory from an original set that is allowed within the theory. Now, the only set at the moment that's allowed within our theory is the empty set. So what we can do then to create new sets is successively take power sets. So if we consider the power set of the empty set, well, there's only one subset of the empty set, and that is the empty set. So the power set of the empty set is just going to be the set containing the empty set. You could also write it like this. So here we have a new set that is allowed to be a set within our theory, just from these two axioms that we've already got. Then we could consider taking the power set of this new set that we've got, and we'd get this. So this now has two subsets. It has the set that contains nothing, so the empty set is a subset, and then it has the set that contains this element, which is the empty set. So it has the set containing the empty set. So the power set of this set is then this set, which contains now two elements. So you can see you've gone from a set that contains 0 elements to a set that contains 1 element to a set that now contains 2 elements. And you could go on like this. So you've now got a huge number, an infinite number in fact, of sets just from these axioms that are actually going to be allowed to be sets within our new theory. Axiom number 3 is called the pairing axiom. And this says that if you have two sets, A and B, that are allowed within the theory to be sets, then you can create a third set out of the two by taking the set that contains the set A and the set B, and that new set is going to be allowed to be a set within our new theory. Now, why is this useful? Well, it's useful in loads of ways, but continuing on our line of thought, we're heading towards what's called the Zermelo construction of the natural numbers. So if we, for instance, take one of the sets that we've managed to construct thus far, so let's take this set here, the set containing the empty set, what we can consider doing is letting both A and B equal this same set. Then by this axiom, the set containing this and this is a new set. Now, by the axiom of extensionality, these two are the same element, so this is equal to this set that just contains the set containing the empty set, because by the axiom of extensionality, these two are equal to one another because they have the same elements. So we've now managed to get this thing here, where we've got 3 set brackets, if you like, whereas this one had 2 set brackets, and obviously the empty set originally had 1 set bracket. And then we could go further. We could imagine trying to get this inside a further set bracket. And the way we can do that is just by making A equal this and B equal this again, and then by the pairing axiom, the set containing those two is a set, but of course, because it's the same element, we can just reduce it down, and that then proves that this thing with 4 set brackets or 3 set brackets and the empty set inside is then also a set. And you can go on like this. You can put as many set brackets around as you like here, and they're all going to be allowed to be sets now in our new theory of set theory. And this is actually what's called the Zermelo construction of the natural numbers, or this is where we're heading towards. We need a few more axioms to get there, the union axiom and the axiom of infinity. But what we can imagine doing is creating new symbols for these structures that we've created. So we'll call the empty set the symbol 0. We'll call the set containing the empty set the symbol 1. We'll call the set containing the empty set 2. We'll call this one then 3. So you'll use these symbols in the way that you've always been brought up to use them. So when you've got n set brackets around the empty set, that will be identified with the nth natural number. And this is indeed how we're going to construct the natural numbers. There are multiple ways of constructing the natural numbers. This one is what's called the Zermelo construction of the natural numbers. There is also the von Neumann construction of the natural numbers, which is often preferred because it's more obvious the ordering properties on that one. But this one is actually simpler in terms of set theoretic construction, so we'll stick to this one for now. Next axiom then, so axiom number 4 is called the union axiom, and again this is very simple. It says that if you have two sets, A and B, that are allowed within your theory, then you can get a third set that is allowed as a set within your theory by unioning the two together. So A union B is also going to be a set. Now how does this allow us towards what we're trying to do, which is show that the natural numbers, for instance, is a set that's going to be allowed within our theory? Well, we've already said that we're going to use these symbols, the symbols that we recognise from the natural numbers, to denote these sets that we've managed to construct and show are allowed within our theory. What I want to now point out to you is that actually if you look at what 1 is equal to, it's actually equal to the set containing 0, because 0 is the empty set. And then if you look at what 2 is equal to, it's actually equal to the set containing 1, because this is 1, and you can see that 1's inside there, so it's the set containing 1. 3 then is equal to the set containing 2, and so on. 4 is going to be the set containing 3. So what we can now do is apply our union axiom. So we can union these two sets that are allowed together to get a new set that's going to be allowed. And then that new set we can union to this, etc. So we can union all 4 of these together to get this set 0, 1, 2, 3. So by unioning 1, 2, and 3 and 4 together, we get the set with the first 4 natural numbers. And we can go on, of course, so we can construct sets from 0 to n, and these are going to be allowed within our new set theory. Now, at present, we haven't defined any of the other properties on these sets yet, so they haven't got an ordering, and they haven't got a arithmetic defined on them. There's no addition yet defined on them. At the moment, we're just trying to construct them merely as sets. And the next axiom is going to allow us to say actually that the set of all the natural numbers is going to be allowed to be a set within our new theory. So axiom number 5 is called the axiom of infinity, and this is the axiom that is going to allow the entire set of all natural numbers to be a set in our new theory. So we will define for any x, we'll define x plus 1 to be the set containing x. And of course, that is exactly what we've already been doing when we were using 0 for the empty set, 1 for the set containing the empty set, 2 for the set then containing 1, 3 for the set containing 2, etc. So we're just continuing this on. We're saying that the next one along is just going to be the set containing the one that you've already got. This is, if you like, a recursive definition. And then the axiom of infinity is that the set containing all of these is allowed to be a set. So there exists a set that we might as well call the natural numbers, because that's what it fundamentally is isomorphic to, such that firstly 0 is going to be an element of n. So the first element, the empty set, has to be in there. Indeed, if you don't insist on that, then the whole thing doesn't even start off. So you have to insist that the first element is there, which is the empty set, or what we're calling now 0. And for all elements inside here, the next one along also has to be inside there. So once 0 is inside there, then the set containing 0 has to be inside there. So 1 has to be inside there. And then once 1 is inside there, then the set containing 1 has to be inside there, which is 2. So 2 has to be in there, and so on. 3 has to be in there, 4 has to be in there. In fact, all of them has to be in there. And this axiom is saying that that set that contains all of them exists and is allowed to be a set inside Zermelo-Fraenkel set theory. And what we have just done, this construction of the set of natural numbers, this is called, as I previously said, the Zermelo construction. And there are other constructions. They all end up exactly isomorphic to one another. I like this construction because it's very simple. The von Neumann, or Neumann, I don't know how you pronounce it, construction is slightly more complex initially when you look at it, but has advantages in terms of defining order on the elements. And in fact, I think I'll make a video later on in the playlist on set theory on the natural numbers, where we'll look at the construction of the arithmetic and the construction of the order on the natural numbers. And in that video, we'll be using the von Neumann construction rather than the Zermelo construction because it's more helpful there. But as a first introduction, this one I think is easier to get your head around. So we're doing brilliantly. Just from these axioms that all sound perfectly reasonable, we've managed to arrive at a very important set that is going to give rise to a very important number system in maths. And nowhere in the axioms that we've studied does it look as though something like Russell's set is ever going to be allowed to be a set within our theory. Now, the next axiom that we are going to put in is the corrected version of the axiom of unrestricted comprehension. It's going to be the axiom of restricted comprehension, also called the axiom of subsets. And this is going to allow much more maneuverability in our theory of sets. So previously, when we had the axiom of unrestricted comprehension, we were allowed to define all sorts of sets, loads of different sets. Now, the theory that we've defined so far, the axioms that we've defined so far, it's very rigid. You know, the number of things that we're actually able to do here is very restricted. The number of things we're allowed to call sets is very restricted. So we're going to put in an axiom that's going to allow us to use much broader ranges of rules to define new sets. However, it's going to have one crucial adaptation from the axiom of unrestricted comprehension that is going to fix the whole problem of Russell's paradox. So this is brilliant. This is, if you like, the actual solution to Russell's paradox. So I've written it down here, the axiom of restricted comprehension, also called the axiom of subsets, and there are a number of other names for it as well. This says that if A is a set allowed within our theory, then you can construct a subset from it using any rule you like to choose the elements from the original set that are going to go into the subset, and that new subset is going to be allowed within our theory to be a set. Contrast this to the axiom of unrestricted comprehension, which said that you can use any rule you like to define a set. In this new axiom of restricted comprehension, you can use any rule you like to define a subset, not a set. That's the crucial difference. That's the solution to all of this. So let's examine this in detail. So let's start just with some trivial examples. So if we consider our set of natural numbers that we've just agreed is a set, thanks to the axiom of infinity, then we can consider trying to define a subset of that. So we could consider the set S, which is equal to all elements of that original set, the natural numbers, and the rule that we'll make, that any rule that comes into our head that we'll use is we want x to either equal 3 or x to equal 4. So only two elements satisfy that rule, the elements 3 and the elements 4. So that set containing just 3 and 4, that's going to be allowed to be a set within our new theory. Of course, we could have got that long ago because just from the union axiom, we could have unioned the set containing 3 and the set containing 4 together and got that that was a set. So we haven't gained anything new. We already knew this was a set, but that's an example of applying this axiom and obtaining a subset that is allowed to be a set. We could do it again. So we could consider now S prime, which is going to be a subset of this set, S. So it's going to be the elements of X within S such that they obey this rule, and the rule this time is some nonsense that I came up with, that the element has to be red. And of course, neither of these elements are red, they're white here, so none of them obey that, so there's going to be no elements in this subset, so it's going to be equal to the empty set, and of course we know the empty set is already an allowed set within our theory, so it certainly hasn't broken any of the former axioms yet. So let's now try a more difficult example. Let's think of that rule that under the axiom of unrestricted comprehension gave rise to the horrific problem, and let's now apply it here. So let's consider again the set R, Russell's set, but this time it has to be a subset, so we'll use our big set of natural numbers, so elements from the natural numbers, and now they have to obey this rule that they are not contained within themselves. Well, if you remember the way each of those natural numbers were defined, they were sets, but they were sets containing the natural number prior to them. So for instance, 4 was the set containing 3, 10 was the set containing 9. So each of them, although it contains lots of nested sets inside it, it doesn't actually contain itself. So it's not the set containing x, it's the set containing x minus 1. So it doesn't contain itself. So in fact, all of the elements of the natural numbers obey this criterion, and therefore we would get the whole set back again. So now we can ask the question, is R going to be inside itself? Well, the answer is no, because R is not inside the natural numbers. So quite clearly, the answer is no, because this has to be a subset of the natural numbers. Now consider that we were taking a subset of a set that did contain R. What would happen then? So if we had the natural numbers union this set containing R, and we were taking instead the subset of this, so imagine now instead of n we've got n union R here, we'd actually be faced then with the same problem, because R could neither be inside itself nor outside of itself, because if it was inside itself then it shouldn't be inside itself because it contains itself, but if it's outside of itself then it should be inside of itself because it doesn't contain itself. So we're saved by the fact that R cannot be inside of here, because this had to be a set that was already defined within our other axioms, and our other axioms would never have allowed R to be defined, so it's not going to be inside here. That's what saves this, the fact that R isn't able to be defined yet by the other axioms. So this is nonsense. It hasn't been allowed within the theory yet. So we're saved by the fact that you're only allowed to use whatever rule you want to create a subset of a set that's already allowed within our theory. You're not allowed to just define a set using whatever rule you want. And that's how we've changed the law of unrestricted comprehension into the law of restricted comprehension, and that saves the theory from this inconsistency from Russell's paradox, whilst still allowing us a lot of freedom to use whatever rule we want to define subsets. So we're about to end the video. Before I end the video, I would just like to say something about the axiom of choice. So this is actually axiom number 10 in Zermelo-Fraenkel Set Theory. We have skipped out axioms 7, 8 and 9. They are complicated and they come from you needing more and more complicated sets to be allowed in mathematics. So as you're trying to build more and more complicated number systems, additional axioms are needed, and those are axioms 7, 8 and 9. We're not going to discuss those in this video. I'm hoping to make more videos in this playlist on set theory, and we'll go into those axioms later with the proper motivation for them. The axiom of choice is axiom number 10, and it's actually the most controversial of all the axioms. In fact, some people refuse to accept it. So there are two strains of Zermelo-Fraenkel set theory. ZF set theory, just standing for Zermelo-Fraenkel set theory, means the first 9 axioms of set theory, whereas ZFC means Zermelo-Fraenkel plus the axiom of choice, so with axiom number 10 allowed, the axiom of choice. And the reason I wanted to bring the axiom of choice up at this point is really just to compare and contrast it to the axiom of subsets that we've just talked about. So the axiom of subsets allows you to pick out a single element from a set and put it in a set by itself. So if we take an example, so here's a set, the set containing 1, 2, and the set containing 1, 2 also is an element inside our set. So we could consider a subset S prime that we're going to have containing only one element that we've picked out of this set, and it would be defined like so. the element is from the original set S, and it obeys this rule that x is equal to 2. So we've got a specific rule for picking out an element. We pick out that element 2, the only element that obeys that rule, and then put it in a set, and that's our subset containing a single element. And the subset axiom tells us that we can do that, and that this thing that we get will be a set itself. The axiom of choice tells you something very similar but with a crucial difference. It tells you that whatever set you have, you are able to pick out an element from that as a representative of that set without any rule needed whatsoever. That's the axiom of choice. I'll say that again, that whatever set you have, it is always possible to pick out an element from that set, and it could be any of those elements. You're just looking for a representative, so you can pick randomly a representative and use that as the representative for the set, and you don't need any rule for picking out that element. That is the axiom of choice, that it's possible to get a representative without a rule for selection. In contrast, the axiom of subsets, it can pick out a single element from a set as well, but it requires a rule in order to pick that element out. So I've written that down here. So the axiom of choice is that it's always possible to select an element out of a non-empty set, even without a rule for selection. And the point that I didn't say earlier is that clearly the set needs to be non-empty for this to apply. If the set has no elements, then it's not going to be possible to pick an element out of it. However, if you have a non-empty set, the axiom of choice is that it is always possible to pick an element out of that set as a representative, even if I don't give you a rule for how to actually pick that element. And that's not something that the axiom of subsets allows you to do. It can do it if you have a rule for selection. But the hypothesis, the axiom that allows you to do it without a rule is called the axiom of choice, and it is controversial. Some people think this is nonsense. How can you actually select an element without a rule? And it does lead to certain problems in maths. Certain very famous paradoxes arise from this, which is why some people don't accept it. We're not going to go into that here. It's very, very complex. But the main point that I raised this for is just to highlight how this is different to the axiom of subsets. So thank you for watching, and I hope that you feel that you've gained something.